Hello. In this screencast, we're going to talk about solving equations. I want to remind you, as we get started, that solving an equation means finding any and all of the numbers that when you plug them in for the variable or variables makes a true statement. So throughout today's screencast, I want you to be keeping that in mind, that we're looking for all of the numbers, not just one, but all of the numbers that make a true statement. In these three warm-up questions, I'd like for you to work through. We're going to check to see if you remember how to solve some of the basic examples of equations before we get into some of the not so basic, and if you remember some of the factoring techniques that we've worked before, specifically in number 2, factoring out a couple of our basic techniques. So go ahead and pause the video, go through the warm-ups, and then once you're done, you can hit play and we will discuss the answers. All right, so hopefully you've had time to work the warm-up questions. And in number 1, it's just a matter of doing some simple inverse operations. We add 3 to both sides, we get 5y equals 3. Divide both sides by 5, we get y equals 5/3. So as I mentioned a moment ago, that number in this case that gives us a true statement would be y equals 5/3. If I plug that back in, 3/5, excuse me. If I plug that back in, I'll get myself a true statement. Now, you might have heard me pause just there and kind of look at my stupid answer that I had written down. And that's actually a good thing. Honestly, I didn't mean to do that. But as you're giving an answer, always go back and visually check. So like I was looking at that, I think it was 5/3 is what I had written down. I looked back over here, and if I had plugged that in, it most definitely was not going to work out. So just do a real quick visual check, and even a dum-dum like me can catch his mistakes if you do that type of visual check. So apologize for that oversight, but I'm glad we caught it. Number 2 is just a matter of factoring out. So that means to write it as a product. And in this case, we said it's just some of the simple basic factoring techniques. The first one of which is a GCF of n. So we take that out. We got n squared minus 9n minus 22. And then I need to factor that a little bit further. There's 2 factors of negative 22 that add up to negative 9. And those 2 factors would be looks like a negative 11 and a positive 2. So I could say there's the n, the GCF, and then an n minus 11, and then an n plus 2. And as I mentioned a moment ago, you could certainly check your answer in this case by foiling it out and then distributing the n back in place, and you get what you started with. On this third and final of the warm-ups, hopefully you had an opportunity to think about or to look back up function notation. F of 3 in this case just means, hey, where x was, now I see a 3. So instead of 8 times x, it's 8 times 3 in my rule. And so 8 times 3 is 24. 24 minus that 16 is going to give us 8. So that's what we find for f of 3. And this says solve for f of x equals 0. Now we're back to that same type of equation solving method that we talked about earlier. In this case, f of x equals 0 means I've got 0 equals 8x minus 16. Add 16 to both sides, divide by 8, and you get x equals 2, which would be, again, something pretty simple to find. So with those warm-ups underway, you look at your learning objectives for today. We're going to be making use of the zero product property, but we're going to do so in the context of solving some quadratic equations. I will remind you in just a bit about what quadratic equations mean. And some of you might not have heard the phrase zero product property before, but this idea of the zero product property is something that is of the utmost importance for us in this unit. So we want to make sure we understand that, and then we'll look past the quadratics at some polynomial functions. So as I scroll down here, I've got 2 very important notions on the screen. You definitely, the things that are boxed in blue and with red stars around, you definitely want to make note of those. The first one's called the zero product property, and pretty much what it says is that if I've got a product set equal to 0, then I can set each individual factor from that product equal to 0. So A equals 0 or B equals 0. And you'll see me sort of outline that step throughout the process of several of these problems. Now this notion of the IFF, that stands for if and only if. And what that means is that this is equivalent of saying it's a two-way street. Okay, so this property works 2 ways. So the way I've read it initially is that we could move from left to right. We could say if I have a product set equal to 0, then I can conclude that each individual factor equals 0. But it also works the other way as well. This is zero product property. If I know that 2 individual things like A and B both equal 0, then of course I can conclude that their product equals 0. And that would come when we're sort of working some of these examples backwards. So we'll probably use that in a later video or later example in this video. The expression I've got down here, or the terms rather, polynomial equations, we're going to be solving these, so we need to understand what a polynomial equation is. In your notes, I'd like for you to write down that a polynomial equation is an equation that's made up of polynomials on the left and or the right side. And remember that polynomials are simply where you've got a combination of numbers and letters with addition, subtraction, and multiplication going on, integral coefficients, and we only have natural number exponents. So nothing kind of kooky like square roots or absolute values or trigonometric functions. These are our basic multiplying by a coefficient and raising x to a particular power, like x to the first, x to the second, x to the third. One thing you'll note is that I've got a fundamental theorem down here. It's called the fundamental theorem of algebra, and it says pretty much that if you can spot the degree of a polynomial equation, then you know how many answers there will be. So in this first little example, it's a degree of 1. The degree means the highest exponent of any one term, or the highest degree of any one term. So there's a degree of 1, and so therefore we have one solution. Here in the second example, we've got a quadratic equation. There's going to be 2 solutions because it's degree 2. And over here, a cubic equation, that means that there's going to be 3 solutions. Now at this point in your game, if you're taking Algebra 1, you probably can find the solution to any linear equation. And you could probably, if it factors at least at this point, find both solutions to a quadratic equation. And there are even some cubic equations that you could find all 3 solutions to, as I've drawn out here with x cubed equals x. However, there will be some equations, polynomial equations, mind you, that you can't find all the solutions for. And that's okay. The theorem doesn't say you can find them all, that they're all real, or that they all are unique. It just says that there are n solutions to a degree n polynomial equation. And so that's going to be very useful for us moving into some of these examples. So like you look at example 1 and you notice, hey, look, there's it's a degree 2. So right out of the gate, I already know from our fundamental theorem of algebra that I should expect to find 2 answers to this one. All right. Now, the whole way that the zero product property works is it is predicated upon your ability to use the factoring, that we've been studying in the last 4 sections of this chapter. I ought to be able to factor this polynomial expression as it's written up here very quickly and very easily. So for example, x minus 3, x plus 1, that's how that factors out. That's just a regular trinomial. It's a FOIL backwards. And so now I've written it as a product. And you'll remember that the zero product property says if you've got a times b equals 0, then either a equals 0 or b equals 0. And, now that just begs the question, well, what is my quote a value? Here's what a is, and here's what b is. So the way to kind of get through all of this, and you guys will use this property enough, we'll use it dozens and dozens of times over the course of this year alone, is you just set each individual factor equal to 0. X minus 3 equals 0. And then we could say x plus 1 equals 0. All right, so those are our 2 answers. So x is going to equal, if I add 3 to both sides, x is going to equal 3, or x is going to equal -1. And those are our 2 answers. You could write them like this, as I've expressed with the or in between. You've seen some texts, I'm sure, some teachers even that maybe will get a little bit fancy and will use a solution set kind of notation. Either one of those is fine. I really don't care. Just make sure that you give me all of the answers. Okay. So that's the first example using the zero product property. Let's look at our second example, and it differs from the first example in that with the first example, it was set equal to 0 already. And I tell students this all the time. The primary goal of using the zero product property is to remember that it is the zero product property. So for example 2, I need to set it equal to 0. And I can simply do that by moving these other 2 terms over to the left side. That's just personal preference. I like to leave the quadratic term positive whenever I can. So I'm going to subtract 13y from both sides, subtract 45 from both sides, and now I'm poised to use the zero product property if, as we mentioned before, if I can comfortably factor this out. Now you might be thinking to yourself, well, Coach Morgan, you're moving a little bit quickly with that factoring. We've just first learned it. How do I figure out, from our first example, for instance, how do I figure out my 2 factors? Well, if you have practiced enough and you feel comfortable going ahead and jumping on in and saying, well, those are my 2 factors, that's great. If not, then just take a sort of a time out almost and just say, hey, over here in the margin, like a little sidebar, I want to figure out what my factorization is for this particular polynomial. All right, you don't have to be in the context of the equation. You can just say, let me figure this one out on the side, and then I'll come back over here, and I'll write up my two factors and go ahead and roll through the zero product property, the ZPP. Okay, so over here in orange, let's do that. And if you want, you can kind of challenge yourself, pause the video, and see if you can come up with the same two factors that I come up with here. All right, so I'll quietly work this one, and I'm going to use what I refer to in class as the magic method, where our text refers it to as the AC method. So I've multiplied 2 times negative 45, and now I'm just going to look for two factors of 90 that add up to 13. And I want to say maybe 15. No, not 15. Let me think about this for a moment. All right, so I paused my recording just for a moment and came up with my list of factors just because I didn't want to sit and waste time on the screencast here. And you can tell what I've done is I've made my full list of factors out, and I've found obviously that the pair that will work now for me is the 5 and the 18. The question is, since it's a negative 90, which one should I use? I definitely want the 18 to be negative, since that 13 is negative right there. So this one would factor out as y plus 5. Y minus 18, and then per the magic method here, as I've instructed you guys before, I'd bring the 2 back. It's common over here, so we'd kill it off, and then we would have our two factors. We got 2y plus 5, and we've got y minus 9. And so that little sidebar over there in orange was just some scratch work. I mean, literally, it just took maybe a minute or two to kind of come up with the two factors here, the two binomial factors. And now we can set about using our zero product property. And that ZPP, again, we get comfortable using it here. We get 2y plus 5 equals 0. Y minus 9 equals 0. And my goal for you guys is to be able to actually jump over that step and to go right on into saying, okay, well, here are my answers. Y is going to be negative 5 halves, or y is going to be positive 9. And you say, well, okay, well, how in the world did you pull that together? It's just a matter of saying, if there's this coefficient in front of the y, your answer is going to have a fraction in it. And if we've got nothing but like y minus 9, if there's a coefficient of 1 in front of my variable, then I know my answer is going to be an integer. So take your time, solve it out until you get comfortable doing it in your head. Now, example 3 is for you guys to try. So I'll leave example 3 for you. Go ahead and pause the video, and you can pick back up once you've done it and see how you do. All right, excellent. So I hope you've had time to work this one out. Again, this is the zero product property. So first step is going to be to solve for 0, or to set 0 on one side. So we subtract 49, and it sounds or it looks rather like a difference of two squares. So we would factor it out as 5z minus 7 and 5z plus 7. I like to put my plus first. And then from the zero product property, I'm going to get my two answers of plus or minus 7/5, right? And hopefully you can tell at this point we're getting a little bit more comfortable doing even a two-step in my head where I say 5z plus 7 equals 0. What would that take? I would have to subtract 7 and divide both sides by 5. And that's where we get that 7/5, just like we saw in the warm-up using a couple of inverse operations. The plus or minus saves a little bit of space, since with this other one right here, I would add 7 to both sides. Plus or minus just allows me to express both of those answers in one short, sweet expression there. All right, example 4, we start throwing in a little bit of some curveballs. Example 4 has set up where we need to FOIL it out first. So I need to go ahead and multiply 3x times x. The outer is going to give me -3. The inner is going to give me -8. So that's going to be -11x. And then the last times the last is going to be +8. And then let's go ahead and subtract 3x from both sides to set it equal to 0. These two linear terms are going to come together, and it's going to give me 3x squared minus 14x plus 8 equals 0. This is again another magic method problem, so we've got the factor of 24. And actually, I'll show you the British method, since in class we've talked before about all three of those methods, trial and error, British, and AC. I need to split up. 3 times 8 is 24, and two factors that add up to 14. Let's see here, 1, 24, 2, and 12. That'll do it, 2 and 12. So let's say minus 2x minus 12x, and then plus 8 equals 0. We'll do this one by grouping, and that'll give us another example to have under our belts for grouping in the British method. Looks like we'll factor out an x, 3x minus 2. We'll factor out a negative 4, and leave us with 3x minus 2. And therefore, we've got x minus 4 and 3x minus 2 are our two factors. So that's actually what I'll write up over here, just to be consistent with how I'm working things. X minus 4 and 3x minus 2. And then I want you to try and guess, what are my answers going to be here? Well, from that binomial, x is going to equal 4. Or, from this binomial, x will equal 2/3. And so we've got our two answers. All right, so those are our two answers. And example 5, I'd like for you to try. So you can pause the video, work that one out on your own. Again, I'll caution you, FOIL at the beginning, and then subtract 8, and then FOIL again. And once you've done that, you'll end up hopefully with a k equals plus or minus 3. Now, interestingly enough, I mentioned at the very beginning of this screencast, you can check your answers by plugging it back into the very beginning of the problem. And I want you to try and do that with me right now. If we plugged in 3 for k, 3 plus 1, and 3 minus 1 would yield 4 times 2, which does indeed, equal that 8 that we were checking. And then what happens if I multiply, or rather if I plug in a negative 3? Well, if I plug in a negative 3, I wind up with a negative 2 and a negative 4, which negative 2 times negative 4 again checks out to equal 8. So both of those answers are legitimate, and it's a good way for you to get into the habit of checking your answers. Later on, we'll start looking at some equations where perhaps the answers that we get aren't legitimate. Now, on we go with the discussion of what's known as multiplicity. All right, now multiplicity is how many times a particular solution is repeated. And I want to make mention of some vocabulary right quick. The word solution, the word root, and the word zero are all synonyms in this context. When we're asked to solve an equation, like here in example 6, we're asked to solve this equation. It's a degree 3. It's a cubic polynomial equation. There's going to be 3 answers. That's how many there's going to be from the fundamental theorem of algebra. And the answer or the root or the zero or the solution, that just means the same thing. There's 3 of those bad boys. There's 3 roots that we're looking for. And the way that we go about solving this equation is, in fact, very similar, if not exactly like some of the earlier ones that we've looked at, where I subtract 60m squared from both sides to put it in a nice, neat format, and then I go to town factoring it. You might notice in this case that there's a factor of m that could be taken out. We're left with 9m squared minus 60m plus 100. And then hopefully if you've got your wits about you, you'll notice that looks like a perfect square trinomial. And in fact, when I'm splitting it up like this, just as we've done in class, we multiply 3m times 10 to get 30m, and that checks out. So we've got m, we've got 3m minus 10 quantity squared equals 0. And actually, let me give myself a little bit more room here. The idea is that, we could have written out 3m minus 10 a couple of times. And in fact, some students prefer doing that. And if you do that, it really does spell out for you the fact that this is a double root, or it has a multiplicity, to use that vocabulary word, where it's repeated twice. Here, m simply equals 0. There is no work for me to do there. And in this case, 3m minus 10 equals 0 from our ZPP. So very quickly, we could at this point say add 10, divide by 3. And there are my answers. There are my roots. And again, go back to the question. It says, how many are there? Well, there are 3 of them. That's very strange, because you see right there, you see 2 numbers. In fact, if I wrote up my solution set, if I wrote m equals, fellas, all I'm putting in there is a 0 and a 10 cubed, okay? But this 10 cubed is what's called a double root, or a double 0 or a double solution. Most of the time it would just be referred to as a double root in that context, because if you had written it out instead of 3m minus 10 quantity squared, if you had written it out as 3m minus 10 times 3m minus 10, then you would have gotten that same answer over again. Having used the ZPP, you'd have an identical equation and therefore an identical root. Now you do not have to include that root twice. That's being a bit redundant. All you have to do is say, hey, here are my roots, here are my solutions, 0, 10/3. Now later on in your math classes, if you're taking Algebra 2, you'll learn how multiplicity can affect the graph of a polynomial. When you get to that point, this hopefully will come back to you. But let's look at one final example here, and then the lesson will be yours. It's example 7 says, hey, here's this given function. Find x when f of x equals 6. Well, all they're asking you to do is to set f of x equal to 6 and solve. And then this becomes, just like we saw in some earlier examples, a matter of just, hey, set it equal to 0 by subtracting 6 from both sides, plus 2x minus 8. And then we could factor that out as x plus 4x minus 2. And per the zero product property, we wind up with x equals -4, or x equals +2. So we've answered part A, and you look at part B, it says find 2 points that lie on the graph of the function. We've already done that too. You might not realize it, but the function itself is a quadratic function, okay? And it's going to have, actually, let me put it this way. It's going to have you hopefully remember graphing out parabolas. The ax squared plus bx plus c tells us this general format for a quadratic equation. It's going to tell us where the vertex occurs. It occurs at the opposite of b over 2a, so that's -2 over 2, which is -1. So I know that the vertex is going to lie on this vertical line over here, and it would just be a simple matter of saying, okay, hey, what's f of -1 to figure out the corresponding y-coordinate. Let's see here, -1 squared is 1, -2 minus 2 looks like -3. 1, 2, 3. That's where that vertex is going to be. And so this curvature here looks very much like what we practiced doing in the first semester as far as graphing parabolas. But the reason I wanted to put a quick graph together is, if you note, look at what x equals -4 and x equals +2 generate for us, okay? So like if I went over to x equals 2, 3, 4, 5, 6. There's the point right there where the function equaled 6. In other words, its y value is 6. So 2, 6 is a point that's on the curve. As is -4. My graph is not as accurate as it should be, but this idea of -4, 6 is also on the graph. And we didn't really have to graph the function to already know that, hey, the x-coordinate here is -4 when the y-coordinate is 6, and then the same thing, the x-coordinate being 2, when the y-coordinate is 6. We'll talk more about that in a later class. There are some more examples to try on your own from our text, but I feel like you guys have gotten enough in this screencast to at least get you started on the homework, which I've got posted online. So thank you for watching, and I look forward to seeing you again in class tomorrow.